So in the last class, we explained various kind of directions of the stresses and all the three kinds of normal stresses that can be there. So I can go back to that slide and explain it a little bit more probably. The slide is here. Okay. Yeah. All right. So that's what we were discussing, that stresses in if you assume a point, and then if you assume a small q around that point, a very small area around the point, you take a very small q, and then this is the point, let's say, and you assume a very small cube around that point, you get something like this, and then that cube will have 6 faces, right? These 6 faces will have normal stresses at each of these faces. So there will be 6 normal stresses around that. But when you look at a single point, there are no 6 faces, there are only 3 of them, because the opposite side should be equal unless there is a force that is acting at them. Okay? So the unknown or the state of the stress at that point are 3 of them only: sigma xx, sigma yy, and sigma zz. Each of these stress is along the direction. So the face, this one, that one I'm drawing here, has a direction that is normal along x, and the force that is causing this sigma is also along x, right? So that come out to be sigma xx. Similarly, sigma yy and sigma zz. So these are the 3 normal forces at a point, right, in a continuum body. Same way, we have looked into shear stresses, and we said there are 6 shear stresses, right, along various surfaces, right? Each of the face will have 2 shear stress, because there will be 2 direction of forces that is grazing the surfaces, right? Like here, there is one that is grazing the surface, the other one that is this one that is grazing through the surface. So each of the face will have 2 of them, right? So there are, if I consider only 3 faces, there are 6 of these forces, stresses, right? Tau xy, tau yx, tau xj, tau zx, tau yz, tau zy. And we have defined also how can you calculate these stresses given the forces along those surfaces. Okay. And then we talked about complementary stresses. We'll talk about complementary stresses again a little bit more when we go into the shear stresses a little bit more details. And yes, we also said there is a Saint variance principle. I saw a demonstration on Saint variance principle today, so I'm not going to talk about this right now. I will talk about this next when I discuss it. Okay. So this is the same figure that we have. You can see that if you have an axial member also, let's say there is an axial member here, which is taken, which is under a force P, and you consider a small point within that domain, and then you consider a small cube. So if you have a small cube and the small, since there are no other forces acting on other directions, it will have one stress along this direction, the other stress along this direction. Both will be sigma xx, and they will be given by P by A. P is the load that is acting on that cross section, and A is the area of cross section. Okay, so it's going to be P by A. And now, as we discussed in the last few classes, that these are all average stresses. They are not point stresses. Okay, although we call it a point stress, they're averaged over the cross section. Shear stress is what we were discussing, going to discuss today. Shear stress is something that actually acts along the surface. So if you can see this picture here, if you see this picture here, okay, there are 2 forces that are acting on this, on this rod or a bar, whatever it is. One along this, the one along this. Okay. Now what will happen? They are just, on the same cross-sectional line. What will happen? If you make them little bit, what should I say, sharper here and sharper there. So let's say it's a sharp thing here and the other one is sharp thing here. What will happen? The rod will start, tearing from this point, right? So if you look at the force will graze to the surface of the tear. This kind of force are called shear force, and the stress that are raised because of this force is called shear stress. Okay, so you can see if I draw a free body diagram here, this force is going to raise to the surface, right? And therefore that is along the surface of this. It's called shear stress. Here also, the average, you have to calculate average, is going to be P, that is this load that is acting, and the area A. So this is the area A. Okay. Examples of this are too many. I gave one example or two examples last class. Here are a few examples, similar examples. On hanger, cloth hanger. Mostly shear stresses in design comes when you try to connect two different kind of bar members together, okay, or when you have connections like gusset plates and all. I gave an example, I think gusset plates here somewhere. I don't remember where it is. So if you see, yeah, here. If you see this structure, this is a bridge structure, right? So the bridge structure will have lot of members coming from different directions. So this is one member. This is one vertical member. This is another inclined member, right? They are all connected at this location. Now these members have to transfer the force to this beam, right? Or to this member. This is a vertical, horizontal member. How are they going to transfer, right? You cannot connect all of them to that member. What you do, you connect using a plate. These plates are called gusset plates. Okay, they are separately designed. They are designed in such a way that they fail before the member fails. So these are all gusset plates. So now this member will be connected to this gusset plate. This member will be connected again to the same gusset plate in this way, and this member will be connected in this way, right? So this gusset plate actually takes all the shear stresses. So if you pull this, it will try to tear this gusset plate out. So it will be something like here. It will be something like this. Okay. It will be something like that. So let's say instead of gusset plate, we have a bolt and nut here. So this bolt and nut is connecting two bars. These two are axial bars, and they are transferring force from each other, right? So this bolt is going to hold them together. Now, if you pull this too high and if you pull that too high, how will the bolt feel? It will try to tear out from you, and this tear out is called shear tear. Okay? It's because of the shear stress in this zone of the material, in this cross section. Right? Now, this is called a single shear, okay, because there is only one force F is acting on the both side, and the tear area is only one. There is only one tear area, so it's a single shear. Similarly, we can have double shear. This is an example of a double shear. Where do you see there is one rod here, one bar here, the other bar is here. So the force is being transferred from this bar to this bar. Okay, so it goes from this bar to these two bars connections, and then from these two bars to here in this one, and then come to this. So if you see this nut bolt, you will see that it can tear from here and here. Right? So there are two surfaces here. One is this one is this one. Similarly, here also there is two surfaces of tear, one this one, this one. So this is one of them. This is a double shear. This is also another double shear. Okay, so there are double plane along which it can shear. So it's a double shear. The free body diagrams are also drawn here. The example, of the stress with a little bit more exaggerated figure is given here. You can see one of them, what is going to happen if this guy is trying to pull this one this side. Let us look at this. If this guy is trying to pull this one this side. So what will happen? This side will move away, and this side is trying to pull this rod, right? It will try to push the rod, and therefore the force will act like this. Now, since this is trying to go this side, this whole rod is trying to go this side. Therefore, this material will try to push this one this side, right? To keep it in equilibrium. So there will be force from this side and this side. So therefore, there are two surfaces along which the crack can happen. The difference between single shear and double shear is, in a single shear, you consider only one side of the area, that means A. In a double shear, since there are two failures, you have to consider two sides of the area. It's 2A. Okay?
Sir?
Yes.
So I understood 1 and 3, sir, but what can you explain to, the second part, sir, like the forces which are acting towards right, sir?
Yeah, Kanika, so I'll explain. Give me 2-3 minutes. I'll show you with a demonstration. Don't worry. Okay?
Okay, sir.
Right. So this is what happens. If there is something else which we need to deal with when we deal with shear stresses or design of nuts and bolts connections, that is bearing stress. Okay, we have to deal with something called bearing stress. I'll explain this also. This has to relate with what you have said. Now, bearing stress is something which you get it as P by A. P is the load that is acting here. Okay. By area is T into D. T is the thickness of the plate and D is the diameter of the hole. Okay. Clear? So that is called bearing stress. I'll give you an explanation why bearing stress is T and D. Just hold on a few minutes. I'll tell you what. Okay. Before we come to this example, let us give you some demonstration on what I wanted to do. Okay. So here is a problem, a truss problem. Okay. The problem is as such given here that the member, this is a two-member truss. There is one member which is the boom, the horizontal member. Its length is 800 mm and its width is 50 mm. Okay. And there is this rod, whose diameter is this. The rod is flattened here to connect with this support, and this is already flattened, so this is connected with this. There is something more here. Okay, there is another connection here which takes a load of 30 kN. So the 30 kN will be connected with another structure with this member. So this rod and this boom member are connected at this joint, and the rod member is connected to this joint, and the boom member is connected to this. And they are both are connected here, along with another connection which carries a load of 30 kN. You have been asked to solve this problem. Okay. It's not difficult to solve because it's a two-member truss and loads are given to you. Right? You can solve it. And once you solve it, you have to design them. You have to check whether the cross sections are fine or not. So allowable sigma, you can assume to be 165 MPa or whatever is given in the notes. First is we need to solve it, right? This part of the solution you have done in engineering mechanics. It's called truss solution. So how to solve it? Method of joints you can use, right? So this joint has 30 kN force, and you have two members. One is CB, another is AB. Okay, and you can solve them to find the forces in this member and this member. Simple. You can do it easily. Otherwise, what you can do is you can find the reaction forces at these two joints. Okay, you can use the static equilibrium condition. So you see MC comes out to be AX to be 40, and CX is equal to minus AX is equal to 40, and AY plus CY is equal to 30 kN. Okay. Now AY and CY cannot be determined from this equation because there are 4 unknown forces, and you can have only 3 forces, 3 equilibrium equations. So you cannot solve it. It's an indeterminate problem. So you have to start solving from this joint. If you start solving from that joint, it's a determinate problem, and you can solve these two. Once you know this force, you can know these two forces and these two forces. Well, okay. So let's say the solution is made. You did the solution, and you got the solution something like this. The force in AB, this member, is 40 kN compressive. Okay. And in BC, it's 50 kN tensile. Compression, this is compression, and this is tensile. Okay. So we know the forces. It's very much, as per the expectation that if you try to load the structure from here, or let's say this work, we try to load the structure from here, what will happen? It will try to pull this, right? It will try to move this way. So this will be in tension, and obviously this will compress, and this will be in compression. So physically also, we can say that the compression and tension that has come to the structure is okay, is at least physically verifiable. All right. Now, we have been asked, can the structure safely support 30 kN of load? So there is a 30 kN of load here. So now, to say that whether the structure will safely support 30 kN of load or not, you have to check the stresses that are there in this member. You have to check the stresses that are there in this member. Okay, these two are going to be normal stresses. They're axial. And you need to check the stresses that are there in the joints, right? The joints can have shear stresses also because it is connected to a plate. You have to check whether those are also okay. That means they are also safe or not. So if AB is given now as 40 kN compression, and if BC is given as 50 kN tension. So at any section, through the member BC. So this is my BC member. So I will write them again here. C is here, B is here, and A is here. So at any section through the BC member, the internal force is 50 kilonewton. Okay. With the force intensity, stress will be there. Sigma BC will be P by A, right? So you know P and you know area because diameter is given to be 20. So if diameter is given 20, D equal to 20. You can find the area, and once you can find the area, you can divide it. So you get sigma BC. So normal stress. So sigma BC is what? It's a normal stress. (159 MPa). What is the allowable stress given to us? Please check. The allowable stress was given was 165 MPa. So the stress that is there in the member BC is lesser than 165. Since conclusion, the strength of the member BC is adequate. Since sigma BC is lesser than sigma allowable. Okay. So the stress that is generated in the member BC is 159 MPa, and the member can carry up to 165 MPa as stress. So the member is well within stress limit, and therefore it is safe. All right. I hope that is understandable. Now let's look at the other part. Now, this part of the problem says that design of the new structure requires selection of appropriate materials and component dimension. Okay. For the reason based on the cost, weight, and availability, choice is made to construct the rod from aluminum 100. Okay. Let's say that it is. So this is a bit different from this problem. In this problem, the stress is given to you. Okay. Maximum stress, allowable stress is given to you, and the member dimension is given to you. Right. Now it is said that you have chosen another material. Okay. Completely different material, whose allowable stress is 100 MPa. So this is a design problem. So the allowable stress has reduced from 165 MPa to 100 MPa. You have been asked to find the diameter at which it will be safe. Okay. Now, since the allowable stress has reduced 150, and we know that the stress in the member with a diameter of 20 mm is 159, so I cannot use 20 mm because in that case 159 is higher than 100. So I have to use something else, some other variable. So sigma allowable should be P by area. Okay, so area is P divided by sigma allowable. I don't know the area because I'm now finding diameter. My 20 mm diameter is no longer safe. So, the area comes out to be this if you divide it. Now, if it's a circular rod, it has to be pi d squared by 4 the area, and therefore d you can find out. So d comes out to be 25.2. Now, can I choose 25? I cannot choose 25 because if I choose 25, my member will fail again. The stress will be higher than 165. So I have to choose something higher than whatever has come to me. So whatever has come is 25. So I have to choose the next higher. I can choose 25.5 or I can choose 26. Okay. So let us choose 26 mm diameter. So this is for a reduced stress. Okay. So first is you have analyzed what is the stress in the thing, and you checked if the allowable stress is within, if the stress developed is within the allowable stress, the system is safe. Then the next question is a design problem that let's say the allowable stress has been reduced to 100. What diameter would you choose? So you solve the inverse problem and get the diameter as 26 mm. Okay, now let's look at the details of the design.
Sir?
Yes.
So will we get these lecture slides, sir? Like these slides?
I can't hear you. Can you be a little clear?
No, so will we get these lecture slides, sir?
I am uploading every day lecture slides. No.
Okay, sir.
Don't you know?
No, sir. I was not aware of that, I guess.
Oh my God! If you go to Google Classroom, okay, I'll show you. After I finish this part of
So no problem, sir. I'll try and see, sir. No problem, sir.
So now the connection here are a little bit involved. You can see the connections. This connection BC member is connected here like this. The plan map is given. So this is the member that was carrying the load. It is transferring the load to the support using this plate. What kind of connection is this? Single shear or double shear? Can anybody tell me?
Single.
Hello?
Single.
Single share. Yes,
Single
right. Very right. You can calculate stress for AB. Why not? If I given you the area, so let's say now this is 30, this is 50. You check it. Jai has asked. Yes, Jai, you check it. No. So we know the load here. The load in the AB member is 40. I think 40, right? I have done it here. Yeah, sigma BC is done, and sigma A. It's not done here. So you can do it. It's not. It will be the same way you have to do it. So it will be.
Okay, sir.
Sigma.
I was confused because it is compression. I was confused that we don't have to calculate.
No. Even for compression, you have to calculate. They may fail in compression also.
Okay.
Area AB. Okay. That you have to. See, most of the, I'll tell you this, please note it down. Most of the metal structure will have similar compression and tensile maximum allowable stress. Okay, most of the metal materials. So 165 in tensile, it will be 165 allowable stress in compression also. But non-metallic composites like wood or like concrete, they will have different values in compression and tension for allowance. Okay, so in that case, you have to look properly. What is the tension? What is the compression? For example, concrete, if you talk about, concrete will have almost zero in tensile. So you cannot allow any tension in concrete. And in compression, it will be 25 MPa, 40 MPa, 35 MPa, given the conditions. But tensile, all of them will be assumed to be zero. So you cannot give any tension to compression in concrete. Okay, it will be only for compression. It's a compression. Right. So you have to check both for tensile and compression. So right, Jai, you have to check it. Please check it. It's not difficult to do. Now this is a single share, right? Very nice single share. Look at this one. What about this?
Double share.
Yes, this is the double share. Very good. What about this one? Look at a little bit more details.
Double share.
We cannot say so quickly whether it's a double or share because there are a lot of members connecting here. One member is this one. One is this member. One is this member. And then there is this member, right? And there is this member here. This member here. Obviously, it's not single share. We have to calculate that based on what is the load and what is the area you are getting. Okay. Based on that, we'll do. So that is what is done here. We'll check that. So this portion is redrawn here. You can see. This is the rod that is coming here. Okay. This is the rod connection. This is the boom horizontal member connection. Okay. This is the horizontal member connection. You can see it has been, it has been split into two. And this is what is carrying the load. Okay. There is a load, will carry a load like this. Okay. So this is the load carrying members. All right. Okay. So we'll go and check now. So it is all written here. This is the inclined member, inclined rod member. This is the horizontal member, and this is the clip that carries the load. Okay. Now the flattened portion, now we have to check at various sections. We have to check the stresses at this flattened section also. Okay. What is the area at the flattened section? The flattened section will have an area. It is given that this is 20, right? And this is 40, right? This is given 40, and this cross section is given 20, like this. So this is 20 into 40 and minus 25 because there is a hole here of 25. Okay. So the minimum portion is this. You can see here it is drawn. So this is this one. If I draw it elaborately, and then there is a hole which is of diameter 25. So the area that is restricting the force is going to be this much only. This is maximum, right? This is too much. But this is the smallest area that is restricted. What is this area? This cross section, right? Multiplied by this thickness. So the thickness is 20. That is given here. Where is this given? This is given here. Yeah, flat end. This is given 20. So the thickness is 20 into 40 mm minus 25. So 30. 300. Now sigma BC is going to be P by A. P is given as 50. We have solved it earlier. And area comes out to 300. So 167. 167 is higher than allowable. Right? This is higher than allowable. So the system may fail at that cross section. So either you have to reduce the hole size from 25 mm to some other value, or you have to increase the thickness there from 20 to some other value, right? Or you have to increase this portion a little bit more. Something you have to do to make sure that it is safe. Oh, sorry, I have given greater than sign, lesser than sign. Okay, now let's look at other things. Cross-section area of the pins at A, B, and C. Now let us look at the pins. Pins are the, it's same as nut and bolts, right? So we have to look at single shear. So the area of the pin is given. So now you can see this pin. If I draw a free body diagram of the pin, there is one force that is acting here, that is a 50 kilonewton. And then there will be a force acting here that will also be 50 kilonewton, right? Because it has balance. So area is going to be, these pins are of 25 mm diameter. So it's going to be pi 25 by 2 whole square, 491 that comes out to be. And therefore, single shear, it's P by only one area. And you get 102. Okay, it's safe. It is lesser than sigma allowable. If it is of same material, right? So you have to check also the pin may be of different material. So if the sigma allowable of the pin is given, then you have to check with that. Now let us look at this. This is single shear. And this is double. Now at double shear, you have two areas. So this is a 40 kilonewton force that is acting here. So each one of them may have 20, 20 on this direction. But the area is going to be this one and this one. So this P plus P, either you can do this P plus P, that is equal to 40 divided by double the area, or single is okay. So again here P by A, it's come down to 40. So you can write this also 40 divided by into area. Okay. Same thing will come, it will come as 40, and that is also lesser than sigma allowable. So the pins are safe right now. Now look at this one. This pin, this was the pin that was a joint B. So this pin I'm talking about. Okay, this pin, the joint B. As you can see, there are a lot of members. There is one member connecting from here. That is again back here. So 1, 2, 3, 4, and 5. 5 connections, 5 sections are there. So if I go there, 1, 2, 3, 4, and 5. Okay. Now look at the direction of the forces. The vertical load is acting downward vertical. It is acted at 2 joints, right? So it is acted at 2 locations. Okay. Can I take a photo of this? Yeah, probably I can take a photo. Keep it there. All right, let me go here and paste it here so that it becomes easier. That's not the best place. I think this is the best place, right? Oh, what did I do? All right, now I can do this. I don't know, probably I'll delete 2 portions from here later. Let it be here for the time being, for the understanding, yes. So if you see, this 30 kilonewton, is being given by this load and this load. So each one of them will carry 15. Symmetric if I assume. So there is a 15 kilonewton down here and 15 kilonewton down here. Okay, acting at those locations. Now this is the horizontal member, right? So this horizontal member is carrying 40, right? So each one of them will carry 20, 20, right? So 20 here, 20 here. Now remember the horizontal member is in compression. So it will try to push the pin out, right? So the action will be along this direction. the force that is acting on the P will be along that direction. Okay. Another, the rod, inclined rod, it is at an angle, right, 30 or some angle, and that is this one, and it is giving a load of 50 kilonewton. I don't know why it is written 20 here. It should give a load of 50 kilonewton. Was it 20 or was it 50? It's a 50. Then why it is written 20? Yeah, this is the one. So this is the one. It's going to carry 50 kilonewton. We'll check why it is 20. Okay. Now divide the pin at B, into sections to determine the section of largest here. So which portion will have largest? Okay. So let's look at PE at this section. What is the load at this section? So this side there is 15 kilonewton and that side there is 20 kilonewton, right? So there is 115 acting here, 20 kilonewton acting here. PG. What is it doing? This is clear. Okay, this is the bearing stress. Okay. Okay, let's say we have to balance it. Oh, okay. Okay, we have to balance and see, direction of forces. So there is a 15 kilonewton here, there is the 20 kilonewton, and then there is 20. So at G, 15. Now, what is the vertical force that will come here? Okay, here, yeah, you see here. So there is a 15 that is acting downward, okay? And at E, therefore, there will be another 15 that will be acting upward, okay? Now here, if you see G section G. So this section, I know that the force that is acting is 15 kilonewton. The area is same, so it is not going to fail here if it's the load is here higher, right? So let us take a section here like this. If I take a section here, there is a 15 kilonewton that is acting downward. There is a 20 kilonewton that is acting this way. So there has to be some force that will balance these two, right? That will act here. So you take component of these two forces and what you get is 25 kilonewton. Now that 25 kilonewton is more than this 15 kilonewton. Therefore, 25 kilonewton is the highest force that is acting here. Okay. So now the 25 is the highest force and the area of the cross section is going to be, it's earlier we have found it out that 20 into pi d by 2 whole square. So it's going to be 491 again. And if you divide this with this, the 50 is the maximum force that is coming at that section. This is also lesser than sigma allowable. If I assume sigma allowable to be 165 MPa. Okay, is this portion clear? So what you have to do is you have to take sections at every set and see where the maximum force that is acting. Since it's symmetric, the section here will have same force as section here, right? So this one doesn't matter. This actually is 50, and that's why it has come out to 25, half and half, right? So this has to be 50. All right. Okay, now let's go to bearing stress. Now, bearing stress, as we have discussed, is P by load by thickness, okay, into diameter of the hole. Okay, so diameter of the hole is 25. Thickness is given as 30 mm. You see 30 mm thickness is given. So you divide the load by this. This is what is coming, and it's much. It's always bearing stress is always much lower than sigma allowed all the time. So bearing stress at location A in the bracket. So there are two bearing stresses that you have to do because there is one here. The hole is here, right? So one of this, and then the hole is here. So you have to do there also. But there we have 25 here, right? And 25 here is the thickness, and the whole length is whole diameter is also 25. So it's 25 into 25. But 50 has been done here because they have considered both together, right? And the load has also been doubled, because if you consider half and half, then the load here will be 20 and the load here will be another 20, right? Because this carries 40. Right? So load here is 20, right? So if you consider 40, then you have to consider both the areas. So both the areas are considered. It is again lesser than sigma above. So the design is safe till now. Only thing, one place we have crossed the limit is here, 167 MPa. So you have to just change the thickness of one of the bearings. That should be enough. So this is how you solve problem. Please go and I would suggest you to go through this problem in details, write it down, example, explain yourself first, and then you tell me if you have any doubt. Okay, I'll stop here recording.